Hi guys, I made already a few videos that are related to computational statistics. For example, the rejection sampling video, the importance sampling video, etc. But I want to take these videos and make them into a course or a series. So I need to go back a few steps. In this video, I will start with how is it even possible for us to generate random numbers from a distribution using a computer. Specifically, I will talk about generating uniform random numbers and the inverse transform method. So let's start. So our goal is to sample from a random distribution using a computer, okay, which means basically performing simulations. And what is the problem? The problem is that computers are deterministic. So they have a set of instructions and they follow it to the letter. And if you give it a certain input, it will always output the same output. If you give it the same input, the same output will come out of it. And we presume that nature is not deterministic. Yeah, it's a philosophical question a bit, but we won't get into this in this video. And so what can computers give us? They can give us the next best thing, which is pseudo-random numbers. Pseudo-random numbers look like random numbers, meaning it looks like a sequence of numbers that have no pattern in them, but they are in fact will eventually repeat themselves, and they might do have some structure if we look closely. But a good pseudo-random number will be a sequence that is good enough for our purposes. Yeah, so they will act as if they were truly random for our purposes. And our purposes, again, are statistical simulations. Okay, so sampling from random distribution and getting all kinds of properties from these distributions. So all of these pseudo-random numbers, they are generated by a seed. Okay, so you start with some seed, and it can be a truly random quantity. It can be like the current time where you perform the action, or a physical quantity. And then they create a sequence of numbers from that seed. And what this gives you is, if you have the same seed, if you give it the same seed to the algorithm, then you will always get the same sequence. And this is allowing you to achieve some reproducibility to your results. So for example, you do some statistical analysis and you want to reproduce it. So if you put the same seed, you will always get the same sequence and the same results. Now, there is a problem with this. They are usually limited in the number of sequences. So first of all, the sequence will be limited in its length. So after a certain length, it will repeat, but there's also a limited number of different sequences that you can have. So if you start with this seed, you will get this sequence. If you start with another seed, you will get this sequence, but this number is also limited. And now, once we get to the code part, I will also show you in the R programming language that R usually uses the current time. This is what I managed to understand from its source code. And but if you saved your environment, then it will always go back to the seed that you've used in your previous environment. And we will see it in a short while. So I want to give you an example of an algorithm that generates pseudo-random numbers. And it's a very famous algorithm. There are other YouTube videos that already cover it, but I will cover it again. It's called the middle square method. It's an algorithm developed by von Neumann in 1949. And the algorithm is very simple. You choose an even length number. So for example, 2 digits, 4 digits, 6 digits, etc. And you square it. And you always take the middle of the number to be your next number. If the resulting number is not twice the size of the original number, you add zeros to the front. So let's say we start with 34. We square 34, we get 1,156. We take the middle, which is 15, and this is our next number. We take 15, we square it, we get 225. We add 0 because it's not 4, so the number has to be 4 digits. So we add 0, and then we take the middle, which is 22, and we rinse and repeat. Yeah, we do this until eventually we get the same number again. Yeah, so this is the problem with this algorithm. It has a pretty short sequence length. So the length of a sequence can be no longer than 2 to the power 3n. So if I put a 2-digit number, the maximum length is 2 to the power of 6, which is 64. So the maximum length will be less than 64. So maybe it's enough for us. Maybe we only need like 10 random numbers and it's enough for us. But maybe it's not enough for us. Maybe we need much, much more random numbers than just 64 numbers. So we can maybe, give it a bigger seed, have an n to be very large. But still, this is not very good. This is not the state of the art in creating pseudo-random numbers. Another thing you can notice is that it gives you integers. Yeah, it gives you 1 or 2 or 3 or 4 or 5 all the way here to 99. Yeah, and we won't cover all of the integers from 0 to 100 because from 0 to 99 because there's only at max 64. But it gives you only integers. But if we want to transform this into, let's say, a uniform distribution from 0 to 1, then we can just divide it. Sorry, this should be 10 to the power of n. Yeah, so if n is 2, we have to divide by 100. Yeah, okay. But this is not the state of the art. As I said, it's a whole science to create pseudo-random numbers, and I won't go super in-depth in this video. But what R actually uses is a very popular random number generator algorithm called the Mersenne-Twister. And this is the default random generator, but R also supports other algorithms as well. The user can also give it an algorithm, and R will use it. And it uses a seed which have 624 different numbers. Yeah, and it has a sequence length of 2 to the power of 19,937 minus 1, which is an insanely long sequence. And what happens is after you draw 624 samples, then it will create a new seed. Okay, so it will use this vector of seeds for 624 samples, and then it will create a new vector, and again for 624. And this is the source code. As you can see, it's pretty complicated. It's written in C. I won't go into it, but I challenge you, anyone who's watching this video, to go ahead and create a video about this. I would be really happy to understand it. Yeah, and maybe if no one picks up the challenge, then I will try myself in a few months or years. Okay, so this is how you can create a uniform random number. Yeah, I mean, you can create a certain number and certain length, and then if you want to put it in the domain of 0 to 1, you just divide by the biggest number that can be generated, and this transforms this into the domain of 0, 1. Yeah, so we can now sample. Let's imagine that we use the Mersenne-Twister, and we can now have this. We have this black box, and we can always press a button, and it gives us a random number which is uniformly distributed between 0 and 1. But we want to draw samples from other distribution, not just the uniform. So let's say we want to draw from the exponential. So what we can do is something called inverse transform sampling. And we define a transformation. So let's say we have an exponential with some parameter lambda. And we define this transformation over here to be our new variable. It's x. And x is a function of u. Yeah, u is our random variable. X is a random variable, but only because u is a random variable. Yeah. And now we want to know how x distributes. So we look at the CDF of x. And what is the CDF of x at the value small x? It's just the probability that the random variable x is small or equal to the value small x. And what is that? Well, we can just put what x is, which is this quantity over here. And we want to extract the u and to put it in one place and the rest in the other place. And so we get this thing over here. And okay, the probability that u is less or equal to some value. Okay, and what is the CDF of u to be at a certain value? This is our new value now. Well, it depends. If this value is less than 0, the probability is 0. If this value is bigger than 1, then the probability is 1. But if we look at this value, it's 1 minus something. The highest it can go to, well, the highest this can go to is if x is equal to 0. X cannot be negative. If we look here, x is defined as a function of u. And because u is between 0 and 1, then x can only be between 0 and infinity. If u is 0, then x is 0. And if u is 1, then x is infinity, basically. Or let's say if u approaches 1, x approaches infinity. Okay, so this whole quantity can only be between 0 and 1. And so the CDF of a uniform distribution is just this quantity over here. And we got that this is the CDF of x. But surprise, surprise, this CDF is exactly the CDF of an exponential distribution. So by defining this transformation, we got to the exponential distribution. And you might say, wow, you're so smart, you're a genius. How did you come up with it? It's just, I went backward. Yeah, I knew that I have to get this to be in the end what I want. So I started with this, and then I worked my way backward to get what x is as a function of u, and I got what x should be. Yeah. And okay, so this is great. Now we can sample from a uniform distribution, take the value that we got, perform a transformation over it. Yeah, we can just take all the values we got, take 1 minus that value, take the natural log of that quantity divided by our parameter that we want. Let's say if we want from an exponential with parameter 2, then we divide it with 2. Take the minus of that, boom, we have a sample from an exponential distribution. Okay, this is a very simple method. It's also, I think, quite efficient, but unfortunately, this is not how R actually computes the exponential. R uses a different algorithm, which is called the Arens-Dieter algorithm. It's a bit too complicated to explain on the fly. Maybe I will do an entire video just for this algorithm, but it's pretty complex. And to be honest, I'm not sure it's that much needed, because I think the performance differences between this and the inverse transformation algorithm is negligible. But yeah, maybe in the future. Okay, so this is how we would get from a uniform distribution to an exponential distribution. We sample from the exponential distribution. We can also sample from a Bernoulli distribution. This is also pretty easy. We just define a transformation to be an indicator function. Okay, so let's say we want a Bernoulli with some probability p. Our parameter is p, and p can be 0.3, for example. So we say, okay, if if we got a number in u that is below 0.3, so between 0 to 0.3, we give 1. And if we got a number above 0.3, so between 0.3 and 1, we give it 0. Okay, and what is the CDF of that? Well, it's just the probability that x is less or equal to some value little x, and we replace x with its definition, the indicator function. Okay, so let's see. If x is smaller than 0, then the indicator function cannot get values smaller than 0. So the probability of getting a value smaller than 0 is 0. If x is bigger or equal than 1, then of course the indicator function, the maximum value, it only gets 2 values, or either 0 or 1. So with probability 1, it will get at least one of them, and so it will definitely be less or equal than 1. And so if x is between 0 or 1, then let's say x is 0.5, yeah? Then we have a p probability of getting 1, which will be bigger than whatever number it is between 0 and 1. In this case, we chose the number 0.5. Yeah? We have a 1 minus p probability of getting a number above p, yeah? And that way, we will get 0. So x, our indicator function, will give 0 at this point, and this will actually be smaller or equal to 0.5. So this is the result we get for the CDF, and surprise, surprise, this is the CDF of a Bernoulli distribution. In the next video, I will also talk about the normal distribution and maybe also about the Poisson, but I would encourage you to think for yourself, what is maybe the problem with the normal distribution, or what is the challenge with the normal distribution and the inverse transform method. Okay, so I will switch to R. This is how you would call for creating random uniform numbers between 0 and 1. And this is how you would do it for exponential, a normal, a standard normal, a Poisson, etc. In this code over here, I just do the middle square algorithm. I give it some seed. And what I do is I do exactly the algorithm that I described earlier. It's just that I'm also keeping a set of all the numbers that I already produced. And once we reach a number that was already produced, I stop. And also I print the counter of the numbers so far. So if I give it a seed 1, 2, 3, 4, let's see how many numbers it generates. So it generates only 132 numbers. And this is the last number that it generated. Let's give it a different seed and run it again. And this time we only got 62 numbers. This time we only got 80 numbers. I will post the code in the link description. Yeah, and this is the middle square algorithm. Okay, so we said what did R use? We can see if we call this function, this is what R used for creating a uniform random number. And we can also see what is the seed. Okay, so this is the seed. You can see it's 626 numbers long. The first number is some constant, which I'm not sure what it is supposed to be. The second number is a counter. It counts until 624. And once it reaches 624, all these numbers, it changes all these numbers. You can see this is just printing the first 10. And if we set a certain seed, then we get a totally different number. And if we see again the seed, you see that I have 14, the counter is in 14. So what will happen if I add it and I will create more random numbers up to 624? You can see now that the seed has been resetted. And if you give it a seed and then you sample and then set the seed again and sample again, you see we get exactly the same result as before. What I wrote here is that if you will close your program and start again, and you didn't save your environment. So for example, in the global options, okay, you have a possibility to restore the R data into the workspace and to save the R data into the workspace. And this saves also the seed, at least in my case. So if I save the workspace and then run it and open it again, then every time I will open it and the seed will be the same seed. And every time I will open it, this will be the same number. But if you don't do it, then the seed will be the current time of your computer. And so it will always be random. Okay, and now I want to show the inverse transform. So let's say we have, how much is in here? 1 million. And it's the size of 1 million. We create 1 million uniform numbers from 0 to 1. And let's say we want an exponential with a lambda 5. Then we set the lambda and we just create the transform. We take all this vector of 1 million number. From each of these numbers, we take 1 minus that number. We take the minus log of that and divide it by lambda. Okay, here I define the PDF of an exponential with lambda equals 5. And let's see what we got from our sampling. And this is the empirical density of this histogram. And in blue, you get the true PDF of the exponential with a lambda 5. So you can see we got exactly, or almost exactly, the PDF of exponential with lambda equals 5. So good job. This is what we wanted. We wanted to sample from this PDF, and this is the PDF that we got. Okay, and for Bernoulli, let's say p is equal to 0.3, we define an indicator function. Okay, and yeah, so I plotted the empirical PMF. Okay, this is the empirical PMF. You can see that around 0.3 of our samples were 1 and around 0.7 were 0. So this is exactly what we wanted. Yeah, this is the PMF of a Bernoulli. And so, yeah, so this is all I wanted to show you in this video, and I hope you enjoyed, and see you in the next one.